Up until this point, we've been talking only about motion in one dimension. So thus far, we've only talked about one-dimensional motion. That is motion along a line, linear motion. We haven't talked about what happens if an object moves in two dimensions. So two-dimensional motion, that means moving in a plane. So in other words, an object could turn. It could move side to side and up and down, or left and right and forward and backwards. That's moving in a plane. That's two-dimensional motion. And that's our next task, is to extend what we learned previously about one-dimensional motion to now apply it to two-dimensional motion. But before we do that, there's a kind of notation that we need to introduce, and that's going to be the topic of, well, probably the next two videos anyway, sort of a short little mini unit, and that is vectors. So we're going to talk a little bit about vectors. I'm going to introduce vectors right now and talk about how you combine them or add them. So first of all, what is a vector? I think just start with the definition. This might be something that some of you have learned. Sometimes this comes up, for instance, in chemistry class, or even in some cases in some higher level math classes. So a vector is any quantity or measurement that requires two things: size, what we sometimes call magnitude. Magnitude, you might hear me say magnitude. Magnitude just means size. This is usually a number. And direction. I think that's fairly self-explanatory. So if you have a measurement or some kind of quantity that has size and direction, then you've got a vector. So for instance, in our here, so we've got two things. We've got size and direction, or magnitude and direction. So as an example, we've actually talked about a couple of vectors already in this course. When we discussed displacement, we said that the displacement has to have a number and it has to have a sign, positive or negative. The positive and the negative indicated the direction. It could have been direction indicated as, left or right, north or south, whatever, but it requires a direction. Similarly, velocity included direction. You needed a positive or a negative. Acceleration was another one. These are all vectors. They required both a size and a direction. So we've actually already talked about vectors. I just haven't used that word. There are some examples of things that, maybe I'll just put this over here in a box. There are some things that are not vectors. These things are called scalars. So a scalar has no direction. It's just a number, okay? So for instance, some examples of scalars that we talked about like speed. Doesn't have a direction. It's just how fast you're going. There are others like volume. For instance, if I told you I had a gallon of milk, it wouldn't make any sense to say I have a gallon of milk to the left or a gallon of milk east. It's just a number. So there are other things, other quantities called scalars, where you don't need a direction. You just give a number. We represent vectors using arrows. I've sort of hinted at that above right here by putting the arrow there. And you can represent a vector with an arrow. So for instance, I might have an arrow like this. And the length of the arrow here, the length of this arrow represents the size. And I think fairly obviously the arrowhead indicates the direction. So a longer arrow would indicate a greater size vector, and then again, you've got the arrows. And under certain circumstances, you want to add vectors, and there's all sorts of different vectors that you can add. I think maybe we'll start by thinking about the example of a displacement vector. So let's think about some displacement vectors and why you might add them. So I'll maybe start with a new header here. This will be what we call combining vectors. Combining vectors, or sometimes this is called adding vectors. So if I combine vectors, there are basically, we'll split this down into like 4 different ways in which you might combine vectors. And the first 3 are fairly straightforward, and then the 4th gets a little hairy. And in fact, the 4th I might wait until the next video. So the first way we would combine vectors is if they are parallel. So for instance, I might have a vector, and let's imagine it's a displacement. This arrow could be a displacement. Let's say it has 3, we could give it a number, 3, let's say it's 3 miles to the right. What this vector means, just to be clear here, what this vector is indicating when I write an arrow to the right like this here, 3 miles, what I'm saying is you could imagine starting at this point, this is your starting point, and you walk 3 miles. And then you end up at the end of your walk, you end up there. So this, in a sense, right here, you could think about this as like the initial, and this here is the final position. And in a sense, the arrow represents your path. Okay, so that's what we mean when we write a vector in this way. Let me just clear that up. So let's imagine I have one vector here. That's my first one. That's 3 miles to the right. And then maybe I have another one that's 2 miles to the right. So I'll draw it slightly shorter, and I'll write 2 miles. I think it's fairly obvious that if I walked 3 miles to the right and then walked 2 more miles to the right, that the end result here would just be 5 miles to the right. It's not exactly to scale, but that's supposed to be a longer line than either of the 2 starting lines. So that's all you do. If you have 2 vectors pointed in the same direction, if they are parallel, you simply add them up. Second one's fairly straightforward too. That's the case where they are what we would say anti-parallel. So maybe I walk 3 miles to the right, and then I go 2 miles to the left now. And this looks a little weird, but what we're imagining essentially here by combining these is I walk 3 miles to the right, and then I turn around and I walk 2 miles in the opposite direction. Combining these, I think it's clear, I would simply subtract their values, and I would just get 1 mile to the right. Okay? Now, so those are the first 2 cases where I almost probably didn't need to tell you that. You would have figured it out pretty easily on your own. The third case is a little bit more interesting, and that's the case where if I had the 2 vectors which are perpendicular. So for instance, maybe I have my 3 and my 2 again here, and maybe I go 3 miles to the right, and then I go 2 miles down. So that's a right angle. These vectors are perpendicular. Now, one thing I want to point out here, there are 2 ways to combine these vectors. One way is just by drawing the picture as I have. Now, note, when you drawing the picture, so when drawing a diagram, always put vectors, what we say, tip to tail. Tip to tail. What do I mean by that? Well, here's the tip of, I'll zoom in here. Here's the tip of the first vector, and it is matched up with the tail of the other vector, the end. So you don't go the 2 arrowheads together, or you don't go the 2 ends together. You go tip to tail. So this is the tip, and this is a tail. So I've drawn them tip to tail like this. And when you do that, you can simply figure out the total, what you will get when you combine the vectors by simply drawing an arrow from the initial, this is the initial, and ending at the final, like so. So I'll just draw the arrow in like this. So this would be the result of adding those 2 vectors. In fact, it's a result, but in vector terminology, we call this the resultant. The resultant is the vector that you get when you combine the 2 vectors. So I didn't write this, but this is a resultant. Right here, this one. And this one here is also a resultant. So here we have the resultant. And one way to think about the resultant here is you could imagine, let's imagine that you walked 3 miles this way, and then you walked 2 miles this way, and you started here and you ended here. Another way you could have walked to get to the same place would have been to start up here and to simply walk along the resultant. Either way gets you to the same finishing point. If you start up here and you walk 3 miles to the right and 2 miles down, you will end up in the exact same place as if you walked right along this line. That's another way of thinking about it, if these are displacement vectors. So this is one way of combining vectors where you just draw the picture. But you might want to come up with some numbers. So for instance, you might want to know, all right, well, what is the size of the resultant? How do we find out the size of that resultant? Is it 3? Is it 2? Is it more than 3? Is it less than 3? Is it more than 2, less than 2? How do we do that? And some of you, I'm sure, have already realized that since I have a right triangle now and the resultant is the hypotenuse, I can use the Pythagorean theorem. So I'm going to say that the resultant, I'll call the resultant r squared, that's my hypotenuse, equals 3 squared plus 2 squared, okay? So that means r squared is going to be 9 plus 4, which is 13. So r then is just going to be the square root of 13, and I'm not going to go ahead and calculate that out. But we can say that the magnitude, the size of r is 13. So that's one piece of information now that we have given about our resultant vector. We now know that the size is 13. This is the magnitude. Sorry, square root 13 miles. So that's the magnitude. The other thing that we have to give back to our direction, so we've given the size here, but now we've got to give the directions. So what would the direction be? Well, one way to give the direction, or the way that we will give the direction, is by providing an angle. So I want to know what an angle is relative to the starting position. In other words, I might want to know what is this angle, and I'm going to use the Greek letter theta to indicate angle. So this is, some of you may not have seen this before. This is the Greek letter theta, and it's used as a symbol in physics often to indicate an angle. You may have used that in math, or maybe used A, but I'm going to use theta. That's a common thing. So how do I figure out theta? How do I know what this angle right here, how can I figure out what that angle is? This is something that some of you may not have learned. Hopefully most or all of you have, but there's a way of doing this using a trigonometric function, which are, the trigonometric functions are sine, cosine, and tangent. So how do I figure out the direction? How do I figure out theta? I'm going to use sine, cosine, or tangent. These are functions that I'm hoping you're familiar with from geometry class. In this case, what I have here, the angle, I've got the angle here. I'm going to use the 2 and the 3, since those were my starting values. And then if I want to use the 2 and the 3, and I want to know, do I use sine, cosine, or tangent? I'm remembering SOHCAHTOA. I have the 3, which is adjacent, and I've got the 2, which is opposite of the angle. So I want to use the trig function that involves adjacent and opposite, and that one is tangent in SOHCAHTOA. So I could then say, I'll write this out, I could say that the tangent of theta equals the opposite, which is 2, divided by the adjacent, which is 3. And now what we have to do is figure out if the tangent of theta is 2 over 3, then what's theta? And to do this, we have to do the inverse of tangent, which is sometimes called the inverse tangent. Some people call it the arc tangent. On your calculator, it looks like, on the calculator, you'll see it looks like tan to the -1. You usually have to hit a second button and then the tangent button, and you will get that. So I'm going to do that to both sides, and if I do the arctangent of tangent theta, it's just theta. So theta would then equal the arctangent or inverse tangent of 2 over 3, and that's going to be something like 33-ish degrees. You can figure that out, what the exact value is, somewhere between 33 and 34. And now I have given both the size and the direction. I know that the size is square root of 13, And I know the direction is 33 degrees from the starting point right here. This angle here is 33 degrees. All right, I think that's enough for this video. There is a fourth case that we have to discuss, but I think we'll save that for the next video.